that what are the constituents of matter? The answer of this question that varies basically from time to time. For example, as we know earlier, we were have the thinking that the matter at the fundamental level, if we start, for example, at least from the Dalton atomic theory, that matter, if we keep on dividing the matter, then at last it is made up of what is called the atoms. But today we know that atom is not the fundamental constituents. So by fundamental constituent, I means that which cannot be divided further. Okay, that is the ultimate structure. Okay, so what we have today is the picture that atom, they have the electrons which are revolving around, and then there is the nucleus which consists of nucleons. Here by nucleons I mean proton and neutrons, and proton neutron, they are further made of the quark. So this
Excuse me,
answer,
sir.
yes.
So could you please represent, because someone just shared his screen and now
Okay,
yours
okay,
one is like a smaller
okay,
one.
okay.
Thank you.
Is it visible?
Yes, sir. Thank you.
Okay. Okay, so what I was telling that the answer to this question about the fundamental constituents of matter, that change time to time with the advancement in science and technology, right? So how do we understand that whether this particular object or particle that has some further structure or not? How we can explore that? And why it takes so much time that earlier we were thinking that, okay, the matter is made of atom, and now we are with the picture that no, there is something more inside it, right? So if we want to probe some structure, okay, suppose we have some object which has say length L, okay, and if we want to probe it, then we must use some probe, we must incident it with some wave of wavelength lambda, okay, that should be less than the size of the object, that should be comparable or less than the size of the object. For example, if you think about some visible matter, okay, means which is visible with our naked eyes, then we can see that with visible light. But if you want to explore some structure at the length of, for example, delta x, say 10 raised to power minus 5, and more and at more and more small distances, then we need to we need the beams of some energy. For example, at 10 raised to power minus 5 centimeter, we need the energy of at least 2 electron volt, and that is provided with by the microscope. Similarly, if we go on decreasing this length scale, then we will see that, and this value we can find using the de Broglie concept of idea that wavelength can be related to the momenta. Okay, and if we find the value of the energy which we need, then we will see that at very, very small structure, to explore the structure at the level of the nucleus or more inside, we need the high, very high energetic beam, and they can be provided with the accelerators. And therefore, earlier we do not have this facility of high energy beams, and therefore we were not able to explore more inside of the structure of the atom and so. And there is one more reason that why we look for the accelerator or why we need the high energy, because we are familiar with this Einstein mass energy relationship, that energy can be converted into mass and vice versa. So if we have the high energy beams which are taking place, for example, in some collision, then that high energy can be converted into the mass, and we can create the mass, we can create the particle of higher and higher mass, or heavier and heavier particle we can create. And this is the reason that more heavier the particle are, and they are invented recently. Basically, earlier we have the picture of, say, electron, then proton, neutron, and today, if you look into the particle physics data, then you will see many heavier particle, much heavier than what is the mass of your proton and neutron. Okay, so the main message from this is that in order to explore more inside of some matters, okay, some particle, okay, we need the some energy probes, some waves of wavelength lambda, and that can be computed using the de Broglie relationship. Okay, so what I will do next, first of all, I will start with a kind of story, or I will I will give you some feeling of the basically that how different particles came into picture, and in some sense, I will try to summarize the standard model of the particle physics. So, as I told you that earlier there was the Dalton atomic theory. Here, the idea that the elements, they are consisting of the atoms, which atom means indivisible. So that was the picture. But then the model of the J.J. Thomson about the atom, that came into picture when the discovery of the electron through the cathode ray tube take place. And here he observed that a charged beam of the particle that is emitted by the cathode, and then he measured the electron over mass ratio, and he found that the charged beams which are emitted by the cathode, they have very small mass, and they are identified with the electron. And J.J. Thomson came up with the idea of the atom, which we know is the plump pudding model of J.J. Thomson, where he supposed that these electrons, they are like the plum which are pudded, and the positive charge that is uniformly distributed there, and atom as a whole is neutral. Okay, but then the in the case of Rutherford experiment, here he studied the scattering of the alpha ray from the thin gold foil. Then what he observed in that experiment, that was very surprising for him, because if we what he was expecting based on the idea of the model of the atom by J.J. Thomson, that when the scattering of the alpha rays will take place, then the alpha rays, they will be scattered at small angle. But he observed that some of the alpha particles, they were scattered at very large angle. It means they must be scattered from something hard inside there in the atom. Okay, and from there he made the conclusion that there is something called nucleus in the atom, where most of the positive charge that is concentrated, and with this we come up with the idea of the nucleus. And for the case of hydrogen atom, that was named as proton. And after the idea of this Rutherford, or experiment of the Rutherford, Neil Bohr explained the hydrogen atom spectrum, where he considered that electrons, they are revolving around the nucleus, and for in the nucleus we have for the hydrogen atom proton. Now, if we extend this idea of the nucleus and electron which are revolving around the nucleus to the heavier element, say if we talk about, for example, helium, then it was observed that the mass of the helium, that is very heavy. So if the helium has only two protons, and there are two electrons which are revolving around it, then the mass of the helium, that should be equal to two times the mass of proton. But the mass of the helium, that was around four times heavier. It means there is still something which was missing inside the nucleus, and that discrepancy was resolved later by the discovery of the neutron by Chadwick. Okay, so this was some experimental setup for the discovery of the neutron. Here, basically, the alpha beam which are emitted from some radioactive source, then they are incident on the beryllium, and then some uncharged radiations were observed, which when incident on the paraffin wax, then the beam of the protons emerged. Okay, and then scientists, they were trying to understand the nature of these uncharged radiations, and initially they thought that these uncharged radiations, they may be the gamma rays, but the energy they were expecting so that these uncharged radiations could emit the proton, that was not satisfied with those gamma ray. And then the idea of the neutron, that was given by the Chadwick, and he said that okay, these uncharged radiation, they are basically the neutrons, and they have almost the same mass as the mass of proton. And with this, the problem or discrepancy which was there related to the mass of the uh, heavier atoms, that was resolved. Okay, so what happens that up to the 1932, now, there was the picture that the elementary particles, they are of basically four types. One is the proton, neutron, and electron. And also, we are all familiar with the photon. And you know that the photon, that idea came from the black, in explaining the black body radiation spectra, and later photoelectric and Compton effect. Okay, so by the 1932, these were only the elementary particle with which we were familiar with. So by elementary means which do not have some substructure. Okay, so we have the four elementary particle. So the idea, so the picture of the atom was that there is electron which are revolving around the nucleus, and in the nucleus we have these protons and neutrons. And then to explain the stability of this nucleus, okay, the Yukawa theory came into the picture. And so what was that? That if we have a nucleus where we have the protons and they are positively charged, and so there should be some repulsive force between those, and that should make the nucleus unstable. Okay, so then the idea of the strong forces was given through the Yukawa theory, and it was postulated that those nucleons inside the nucleus, nucleons means proton and neutron, they are interacting through some kind of field, and that field is provided by some kind of mesons. They were called the pi mesons at that time, and the potential which was provided by this field, that was this one, minus g square exponential this minus lambda r over r, because the strong force which are holding these nucleons, they are of short range, and therefore this additional factor is there which is responsible for the short range character. Okay, otherwise if you are if we omit this exponential factor from this equation, then this will be simply our Coulomb potential which has a long range character. Okay, and this is basically I have written a reference to the very first paper of the Yukawa related to the meson theory, where he has given the idea of this kind of the potential, and he said that these nucleons inside the nucleus, they are interacting through some field, and that the quanta corresponding to that field, that was called the pi meson. But then at the time when Yukawa proposed this theory, there was no pi meson observed experimentally. Okay, and along that time there was some cosmic ray experiment, and this is the first group, Anderson, Niedermeyer, and the another group was of Street and Stevens. They were studying the cosmic ray particles, and there they observed some particle whose mass was found. They actually, that was a mistake from by them, that they wrongly identified that what the particle they are observing, that is pi meson. But later in 1947, the group of the Powell, they identified that the cosmic rays, they have two kind of particles. One is called pions. Okay, so mass of the pions they observed was around 200 MeV. Even when Yukawa have given this theory, then he postulated that the mass of the pi meson that should be around 200 MeV. Okay, and the actual mass of the pi meson, that is basically around 140 MeV. And the other particle which was observed in the cosmic ray, that was muon. Okay, so these pions, they have the mass between the so if we look for the electron mass and proton mass, then electron, they are the lightest particle, and proton, at that time proton were the heaviest one. So proton were named as baryons, and this pion, they have the mass in between electron and proton, somewhere around 140 MeV. So they were called mesons. So mesons mean something called middle weight, and baryons, they were called heavy weight. And these muons, they came under the category of this leptons. So leptons are lightweight, but the mass of the muon, that is about 207 times the mass of the electron. So if we look at this picture, then so far now we have three kind of particle. One is called light particle, they are called leptons, and the heavier one, they are called baryons, and the middle one, they were called mesons. Okay, so then now I would like to talk about how the idea of the antiparticle came into picture, and that came through the study of the Dirac equation. If we look into the relativistic quantum mechanics, then there we used to study about this relativistic Dirac equation, and if we try to find the solution of that relativistic Dirac equation, then there we used to get this positive and negative energy direct solutions. Okay, energy solutions, and but these negative energy solutions, they were a little bit problematic. Now we will try to understand what was that problem. Suppose these are the positive energy states and these are the negative energy states, and we know that system always try to occupy the state of minimum energy. So whatever the particle you have in the positive energy state, they would try to occupy this negative energy state. So they will come down to the negative energy state, and radiations will be emitted. And in that way, we'll have a radiation catastrophe kind of problem. And to avoid that kind of problem, it was postulated by the in the Dirac hole theory that this negative energy C and that is occupied, and whenever some particle goes from this to the positive energy state, provided this much energy is supplied, then a hole is created, which is identified with the antiparticle of the electron. Okay, so this was basically the initial idea of the antiparticle, which comes into picture theoretically through the problem of the negative energy solution, and the actual explanation of the antiparticle that basically can be found in the quantum field theory through the annihilation and creation operator. So if someone is interested in understanding what is the actual explanation of the Dirac hole theory, then he need to go even beyond the relativistic quantum mechanics to the quantum field theory. Okay, and this antiparticle, the for example, corresponding to the electron, there is the antiparticle positron, and that was observed experimentally in 1931 by the Anderson. So, and this was also now the particle which we have in the picture, which is are known as antiparticle, and corresponding to every particle, there is an antiparticle. Then now I will make you familiar with the neutrinos, that how the idea of neutrino came into the picture. So we are all familiar with beta decay process. Okay, so earlier when the beta decay processes were observed, And if we consider that like a two body decay process, and if we try to find the energy of a particle which is emitted in the two body decay process, then this through this relation we can write the expression of energy, right? And you can see from this equation that whatever the quantities which are appearing in this equation, and they are all constants. Okay, so if we consider the beta decay as a two body decay process, then what we will get the electrons in the beta decay process, they all should have some fixed maximum kinetic energy. However, experimentally, uh, what has been found, if we look for the data for the energy of the electrons which are emitted in the beta decay process, then we observe that electrons of varying energy were observed. Okay, and that can be explained if we consider the beta decay as a three body decay process, and that was first explained by the Pauli, and here he postulated that along with these electrons there is something called neutrinos which are emitted in the beta decay process. Okay, so with this the idea of the neutrino that came into picture. So neutrino, they are very weakly interacting particles, and in the standard model they have mass zeros. What I have written here, nu e, so that is antineutrino corresponding to the electrons. So in the later experiments, other neutrinos were observed. For example, in different decay process. For example, as I told you earlier, that there is something called muon particle which was observed in the cosmic ray, and that was identified as lepton. So corresponding to this muon, there is neutrino that is called muon neutrino. Similarly, later on, as I will talk later, that there is one more this lepton, which is known as tau lepton, and corresponding to the tau lepton, we have the neutrino, which is here denoted by tau neutrino. Okay, and so it has been observed that all the neutrinos, they are left-hander, and antineutrinos, they are the right-handed. So as I told you that in the standard model, the mass of the neutrino is considered zero, but there is some phenomena which is called neutrino oscillations, and that can be explained, okay, if we consider some very small but finite mass of the neutrino. And for the neutrino oscillation, there is already the Nobel Prize given, and that has been observed experimentally also. Okay, so next I will introduce with the particle which are known as the stage one. So at this point, I want to tell you that whatever the particles observed initially in the high energy or particle physics, they were observed through the cosmic rays. So earlier, the study of the particle physics, that was also known as some study of the cosmic ray physics, basically. Okay, so in the cosmic ray study, there were observed some reactions of this type, which has some very strange behavior. Now, what was the strange behavior about these particles? That these particles, which are known as kyons and lambda, so Kyon, that is a basically meson, as we will see, and lambda, that is basically a hypron. So these particles, okay, they were produced on the scale of 10 raised to power minus 23 second, means they were produced through the strong interactions. And whenever they are produced, they are always produced in pairs. So this kind of some particles were
Please unmute.
uh, so this kind of particles which were observed, that it was found that they are always produced in pairs, and when their decay was studied, then it was found that they decay at the scale of 10 raised to power, at time scale of 10 raised to power minus 10 second, which corresponds to some weak decay process. Okay, so that was very strange behavior of about these particles, and that is why they were named as strange particles. And to explain the decay processes of these strange particle, a quantum number known as strangeness was proposed, and it was found that this strangeness quantum number that is conserved in the strong interactions, whereas in the weak reaction weak reactions, this strangeness quantum number is not conserved. Okay, so here, for example, here Kion, lambda, or sigma, sigma zero, these are all known as the strange particles. Okay, so with time now we have, as the studies, with the time we have more and more particles which came into picture, but whatever the particle came into picture in earlier study, they mostly came through the this cosmic ray study. Okay, so with this now we have the picture of the hadrons. So basically, what are hadrons? Hadrons mostly they are identified as the strongly interacting particles. They are classified into two. One is called baryons and another is called mesons. Okay, baryons, they are of two types. One is called nucleons. Under nucleons we have proton and neutrons, and the another one, they are basically today we call them hyperons. And under hyperon the examples are, for example, lambda hyperon, sigma hyperon, or xi hyperon, and many there. Okay, and under the mesons we have many different type of mesons, and some example are pions, kyons, and today we have d mesons, b meson, etc. Okay, so I will later use this word hadron, so that is why I have given this classification, that we should have in our mind that hadrons are some particle which interact strongly, and they are basically of two type, baryons and mesons. Okay, so as you see that with time now we have many and many particles which were coming into the picture, right? So in 1955, when this scientist Willis Lamb, he is the person who has given the idea of the Lamb shift in explaining the hydrogen atom spectrum. So when he got the Nobel Prize for his contribution, then at that time he said that in earlier days, in around 1901 or 1930, when some people, some time scientists, if he invents some particle, then he was awarded Nobel Prize. But now the situation is that so many particles are coming into the picture that if some scientist will identify some new particle, then he must be fined with a $10,000. So that was the craziness that people were it was becoming difficult with the time to understand that why these different particles are coming into picture, and how one can understand the property of these so many particles. Okay, so this is the thing basically then we need in the chemistry. We are familiar with this what is known as the periodic table, where the different elements, they are arranged according to their properties. So is it possible that if we are observing so many particles, then are there some properties which these particles have common? And so is it possible that can we arrange these particles in some pattern, in some structure, so that if some particle are identified or are supposed to follow this particular kind of structure or that particular kind of structure, then they have some similar properties or not? Okay, so we actually need basically some kind of the periodic table so that we could arrange different particles, okay, and we could study their property. And in order to answer this, then the idea of the eightfold Bay came into picture, and that came in around 1961 to 1964. So now remember that so far I haven't talked about the quarks. Okay, so up to this 1964, even up to the 1964, there was no idea of this quarks, right? So whatever I am talking so far about different particles, okay, they are invented, but there was no idea of the quarks, okay. So, what is this eightfold way? So, as I have given the motivation that we want that different particle they should be arranged so that, for example, here if you look, I have written here something called meson octet. So, this is whatever the particle are listed here, they are actually the pseudoscalar mesons. These all particles they have spin 0 and parity -1, right? Similarly, here on the other side, I have baryon octet. So whatever the particle we have in this second figure, they are called baryons. Okay, they have baryon number B is equal to 1. And so other value of the quantum number, for example, what is their strangeness or charge, that is also listed here. And these baryons are the lowest one, okay, the ground state baryons, okay. So this was basically the way that initially the particles were arranged in the eightfold way. So we have meson octet, baryon octet, then we have this decuplet. So in the decuplet, you see that we have so these decuplet they are also basically the baryons, and when this arrangement was found, okay, then at that time this particle was not observed, okay, this, but it was postulated that there should be some particle which has the strangeness -3 and charge -1, and that will occupy this position, okay. And this particle was identified later after postulating this baryon decuplet, okay. So in this way initially the particles were arranged, okay. Pupils they try to arrange the particle so that it become possible to understand their properties. Okay, so now I will move to the idea of the quarks. So again, there was the means some these people, Gelman and Zwing, they were again had some question in their mind that they want to understand that now if some mesons they are following some particular pattern, the baryons they are following some another pattern, then why it is there? Okay, why? So they have given the idea of the quarks that whatever you have the these baryons and mesons, they are made of some more fundamental constituents, and they were called quarks. So when these people proposed the idea of the quarks, then initially they have given the idea of only three quarks: up, down, and strange. Okay, and these were called three flavor of the quarks, and they said that these quarks they also come in three colors. Okay, so if I have a, for example, U quark, then this comes into three color state, which is known as red, green, and blue. And why we need this color state? That can be explained. For example, if we look into this delta baryons, and if we use this picture of the Gelman award, where they have given the idea of the quark, then lambda baryon that will be made of three U quarks, right? And these quarks, if you look into the property of these quarks, then they have spin half, and so three particles of same particles of spin half, they cannot occupy the same state as per the Pauli exclusion principle. And therefore, in order to distinguish between these, the idea of the color was given that a given quark that can have three colors, it means there are three different states basically. Okay, and the naturally occurring objects, by naturally occurring objects mean which are which are finally observed in the experiments. Okay, So baryons, for example, or mesons, they all are colorless. Okay, so for example, if I have a meson, say for example pion or kyon, they are the example of the mesons. A meson that is made of one quark and one anti-quark, right? And baryons, they were observed, they were postulated to be made of three quarks. Okay, so these quark combination will be such that overall they will be colorless, right? So we have to keep in this mind that a baryon that consists of three quarks. Okay, for example, proton here that is made of UDS quarks, so that overall it satisfy the that proton has, for example, plus 1 unit charge. Okay, so that should be the that should be the sum of the charges of these U and D quarks. Okay, so for example, U quark has the charge of plus 2 by 3, and D quark that has the charge of minus 1 by 3. So sum of those that should satisfy the property of the proton. So that was the initial idea where the quarks were proposed theoretically initially by the Gell-Mann. So, and the existence of these quarks that was proved in the experiment. So here I have written this means deep inelastic scattering experiment, right? And these experiment were the initial experiment. This is basically the Stanford Linear Accelerator Center, where the experiment of high energy electron beams, these high energy electron beam, they were scattered from the proton, and when the data related to the this scattering that was studied, then it was observed that the observed data that can be explained only if we consider that inside the proton they have some more substructure. So idea of all these experiment that is same as we have the Rutherford, as I discussed initially, that when Rutherford performed his experiment, then he observed that there is some large, there is the scattering of the alpha particles at some large angle. Similar kind of things were observed in the this slag experiment. For example, this is the thing, means if we have some atom and if it has some substructure, then experimental data was this one, which is here in the form of these black dots. Okay, and if they do not have some substructure, then this straight line should be observed, right? And same was observed for the case of the protons also, and from there it was made the conclusion that there is something more inside the proton, and that was the initial experimental discovery of the light quarks basically. And then later the heavier quarks were also observed. Okay, so with this, now we have the picture that these protons and neutrons, they are made of the quarks. And so initially we have the idea of up, down, and stage quarks. And these were the light quarks which were observed in the initial experiment of the scattering of the electrons from the proton. And also in those experimental facilities, the scattering of the neutrino beams were carried out. And these existence of the light quarks that was proved. Then in 1974, the year of 1974 in the particle physics, that is known as November Revolution. Now, what is this November Revolution? That in 1974, these scientists sitting, they observed some particle which has very heavy mass. Its mass was very large, and that was about 3 times the mass of the proton. Okay, and there were basically two groups who observed this kind of the behavior or this kind of the particle experimentally, and later they announced together this particle, and this was named as J psi. Okay, now there was some very interesting properties about this J psi meson. One thing is that this was very heavier particle, so there was no other particle at that time which has the mass this much, but what is observed for the J psi meson, and its lifetime that was also means long as compared to the lifetime of the strong interactions, and this particle J psi that was identified as meson, and it was found that this meson, now we know that meson that is made of one quark and one anti-quark, and this J psi that was found to made of one C quark. So C here, I mean the charm quark, and C bar mean anti-charm quark. Okay, so with the discovery of J psi meson in 1974, this idea of the fourth quark came into picture, and later in the later experiments other mesons were observed. For example, here D0 or D positive meson, here for example, D0 meson that consists of one charm quark, and another is the light quark. Okay, so with this, with the discovery of these different mesons, and the it was finally confirmed that there is one more quark, and that is called the charm quark. Okay, so as I told earlier that there was also the discovery of the lepton, and that is called the tau lepton, and that was found experimentally in 1975. So if we now look into the picture of the particle, what we have the picture, if we look into the leptons, then we have basically electrons, muons, and tau. Okay, these are the leptons, and correspondingly we have the electron neutrino, muon neutrino, and tau neutrino. And if we look into the quark side, then for the quark we found up, down, charm, stay. Okay, so I should basically write like this, that up, up, down, and then charm, stage. Okay, so it was found that as we have here basically the 8 leptons, then there should be 2 more quarks, so that we could have this kind of the symmetry. Okay, so this is called basically the first generation of the leptons, and then more heavier leptons were observed, and they were called the second generation, and they were called the third generation. Similarly, if you look into the masses of the quarks, then U and D quark, they are the lightest one, and they are called the first generation of the quarks. Then we have S quark, which has experimental mass around 100 or around this 100 MeV. Okay, and C quark that is very heavy basically, but that is known as the second generation of the quark. And then it was it was postulated that there should be 2 more quarks. Okay, and which and they those more 2 more quarks, they will be heavier than these quarks charm and stage. And it was found experimentally later. For example, in 1977, the bottom mesons were formed, were produced experimentally, and similarly there is something called the upsilon mesons, and they consist of the quark which are called bottom quark, B quark or bottom quark, and that has the mass even more than this charm quark. And then the last quark which was observed, and that is called the sixth quark, and that is known as the top quark, and top quark has the mass 174 GeV. So if you look into the mass of, for example, D quark or up quark, that is 5 MeV, 5 mega electron volt. If you look into the quark mass of this stage, that is around 100 MeV, as I told, right? And this mass of the tau quark, that is very, very large. That is about 174 GeV, and that was observed in the experimental facility of Tevatron, where I think this proton-antiproton collisions take place. And if you look into different particles of the particle data booklet, then you will never find any particle which is made of top quark, because this top quark, that because of being very heavy, this is very unstable and its lifetime is very short, and no bond state of top quark is observed. Okay, so with this, now we have this basically the picture of the elementary particle. But we have the picture today that we have these elementary particle electrons, corresponding electron, neutrino, up and down quark. So up and down quark, they our proton, neutron, okay, which are part of the atom. Okay, so they are made the ordinary atom of our universe. They are made of up and down quarks. And then there are other particles also, for example, muons, tau, charms, stains, top, bottom quarks. Okay, and these quarks, they can be produced experimentally in different experimental facilities, or they may have produced, as I will discuss later, something about the Big Bang. Okay, and so these particles may have produced in an earlier stage of the evolution of the universe. So this is basically the answer to the first, but I postulated, means wrote in my very first slide, that what are the ultimate constituents of matter. Okay, so ultimate constituent of the matter. So as of today's understanding, that these are quarks and leptons, and how these quarks and leptons, they interact with each other. So the fundamental forces which I am going to discuss next. So in the standard model, we have electromagnetic forces, weak forces, and strong forces. The fourth force, which we know, the gravitational force, at the subatomic level, this gravitational force is very weak, and therefore we do not include that in the standard model. Okay, so first I will discuss a little about the electromagnetic interaction, and then I will switch to other interactions. Okay, so what is electromagnetic interactions? Means where the interaction between the charged particle, they are mediated through the photon. So this is just this is some Feynman diagram where this vertex point, this is known as the vertex. Okay, so Feynman diagram, basically they are used to study the scattering processes in different interactions. So here, this strength of the electromagnetic interaction, that is characterized by something which is called the fine structure constant. Okay, and we know that the value of the fine structure constant, that is equal to this one, 1 over 137. And at the quantum level, the theory of electromagnetic interaction, that is known as quantum electrodynamic. And this theory that was proposed, that was given by Tomonaga, Suchwinger, and Feynman in 1965. Now, what I have written here, the fine structure constant, and this is written here as a constant value. But if we, this value of the fine structure constant, that is not exactly constant. If we look into the quantum electrodynamic, and if we look for its variation as a function of the energy, then you will see that the fine structure constant, that has some dependence on the energy. However, the dependence on that energy is very weak. For example, at an energy scale of, for example, 91 GeV, the value of the fine structure constant, that become 1 over 128. Okay, so whatever the phenomena we observe basically at, or the energy at which we deal with, this kind of relation, that doesn't play much role, and therefore we usually take this value of the fine structure constant. Okay, and I will come to this picture later on. Similarly, we have the weak interactions, and weak interactions means what I told earlier, the leptons, okay, neutrinos and electrons. So every those process, that process where electron or this neutrinos are involved, they are known as weak interactions. And weak interactions, they are mediated through the mesons, which are known as W plus minus and Z mesons. Okay, so earlier what I listed, electromagnetic interaction, that is mediated through the photon, whereas the weak interaction, they are mediated through the W plus minus and Z bosons. And if we evaluate the structure constant, means that fine structure constant, which characterize the strength of weak interaction, then if you go into the theory of weak interaction in the standard model, then you can see that the value of this fine structure constant, that comes out to be 1 over around 29.5, right? And this value is although large than this. However, if we look into the masses of this W plus minus and Z bosons, they are very heavy. They have the mass around 91 GeV and 80 GeV, and because of that, the propagator which is mediating these weak interaction, in that propagator, mass comes into the denominator, and that become weak, and therefore we have this weak interaction. It is not that the this from this value of the fine structure constant of weak interaction, we cannot infer that these are the weak interactions. Okay, and the final finally, we have this strong interactions. So as we have the idea that proton neutrons, they are made of the quarks. Okay, so these quarks inside the nucleons, okay, they are interacting through the forces which are known as the strong forces, and they are mediated through the particle which we call gluons. So what is written here, the Lagrangian of the this QCD. So if you look into the Lagrangian of the QCD, then here we have this direct part of the Lagrangian, and this is called the mass term. And so if you basically look into the direct Lagrangian, psi bar iota gamma mu del mu minus, so here I can write psi minus m psi bar psi. So this is something the Lagrangian density for the direct particle. So if someone is not familiar with this concept of the Lagrangian densities, then you may recall your, I think, the study of the classical mechanics in your very first semester of MSc Physics, where we used to deal with the Lagrangian and Hamiltonian. And once we have the Lagrangian for the system, we use the equation of motion, which we call the Euler-Lagrange equation. Putting the Lagrange in that, we can obtain the equation of motion, and from that we can study the behavior of the system. Similarly, in the quantum field theories, we can write the Lagrangian density for different particles. So, for example, what I have written here, this is the Lagrangian density for the direct particle. So what I mean by the direct particle being, for example, here in case of QCD, I am dealing with the quarks. So QCD means quantum chromodynamics. So as I told that quarks, they are the colored. So theory corresponding to the study of the interaction of the quarks through the gluons, that is known as the quantum chromodynamics. Okay. So quarks, they have spin half. So they are the direct particle. So if we have a free quark, then we will have this kind of free Lagrangian density. But since quarks are interacting through the gluons, so in the Lagrangian density, we have these terms, which gives the, so this G mu alpha, that gives us basically the gluon field. Okay, it is just like the electrodynamics. In the quantum electrodynamics, we have the electrons, for example, they are the charged particles. They are interacting through the photons. So if you want to write some Lagrangian density for the quantum electrodynamic, so you will write this kind of Lagrangian for the electrons. But along with that, you have to add some term which characterize the interaction of the electron with photon. Similarly, when we are writing the Lagrangian density for the quantum chromodynamic, then so whenever you are writing the Lagrangian density for any system, then first thing we have to identify that in this the system in which some interactions are taking place, then what are those particles which are interacting, right? So corresponding to those different particles, we used to write the Lagrangian terms. Okay, so we have the drag part. So in the QCD, we have the quarks. So they are represented here by this psi, and gluons, which are represented by here G. Okay, and similarly, this is the free part for the free term for the gluon, and that is the basically free interaction. Okay, so that is the free term for the gluon, and G mu, that is the field strength tensor. And these gluons, okay, they are also colored. Okay, so by color I means that they have the charge also, and gluons, they also interact with each other. Okay, that was not the case in the photon. In the case of quantum electrodynamic, we have only one single photon. But when we come to the quantum chromodynamic, then if you go into the detail of this QCD, then you will see that this is called SU3 theory. So by SU3, here 3 mean 3 colors of a quark, right? So that is why it is called SU3. And for this SU3 theory, there are 8 generators, and those generators are identified with 8 gluons basically. And these gluons, they are colored, and therefore they can interact with each other. Okay, so that is one basic difference, and which cause very different behavior of the QED and QCD, that the quanta which is there in the electromagnetic interaction photon, they do not interact with each other, but in quantum chromodynamic, we have the gluons which interact with each other. And therefore, if we look into the fine this structure, or what I call is the coupling constant of the quantum chromodynamic, then this is known as the strong coupling constant, alpha s. That is known as the strong coupling constant. And why it is called so? So in this figure, we have shown this variation of the coupling constant alpha s as a function of the momenta transfer. So what happens with this strong coupling constant, that if you increase the energy or momenta, or if you go in the short distance, what I mean by this, that if you have some, for example, some meson that is made of some quark anti-quark, okay, that is what inside we have the mesons. So if you want to separate those mesons, if you want to isolate the mesons, then what will happen, that the strength of the interaction between these mesons, that will keep on increasing. You cannot separate the quarks, you cannot isolate the quark. The strength of the coupling, that if you plot the coupling as a function of the distance, then as you increase the distance, the strength of the coupling will increase. But in case of the QED, if you increase the distance, if you are moving away from the charge, then the strength of that interaction, that will decrease. And this happens basically because of the colored nature of these quarks, or and not only quarks but gluons. Okay, and that is why we have in the in the QCD, we have something called the quark confinement, according to which we cannot isolate the quarks. Okay, however, if we are increasing the momenta transfer or energy, then our coupling constant will become very small, and in that case we can have a free quark, which is something called asymptotic freedom. So these are two basic properties of the quantum chromodynamic, two terms which we use to which we use normally. One is called quark confinement, means if you have some baryon or some mesons, then quarks are confined in that. You cannot experimentally observe in the detectors three quarks, right? If you try to separate the quark anti-quark pair, then what will happen that the field which is among these quarks through the gluons, okay, the potential will keep on increasing with the distance, and then at some time this potential or energy which is accumulated, that will give rise to the new quark anti-quark pairs, and so again we have some new hadrons or say mesons, for example. Okay, so that is these are two very important properties. Okay, so we can also understand the difference between the QED and QCD through this kind of picture. In QED, so what is done here, that there is something called in the vacuum polarization. So what I mean by vacuum polarization, that the vacuum that is not completely vacuum, but that is populated with the electron positron pairs. Okay, continuously in the vacuum, these electron positron pairs, they are keep on creating and destroying, and they are known as the virtual particle. So if you have some isolated, say if you have some electron, then due to the creation of the electron positron pair in the vacuum, there will be many electron positron pairs inside the around this electron, and then what will happen, that around this electron there will be some positron or E positive, and this kind of layer will be created. And if you have some test charge, if you want to feel this the field of this electron, then this layer that will screen the effect of this electron basically. So if you penetrate more inside, if you decrease the distance, then you will be able to feel more strength of interaction. Okay, and whereas in the QCD, along with this, so corresponding to the electrons, now we have here the quarks, so there will be quark polarization, but along with the quark polarization, now we have the gluons which are colored, and those gluons, they dominate over the quark polarization, and therefore the behavior of the coupling constant in the QCD, that is different as compared to the QED. Okay, so with this we have this final picture of the standard model, where we have the these elementary particle leptons and quarks, and the interactions, they takes place through the gluons for the quantum chromodynamic, and for the other we have this photon and W and Z bosons, and there is something called Higgs boson which is observed now experimentally, and that is responsible for the masses of different particles through something called the Higgs mechanism. Okay, so I think I need some more time. Is it okay with the organizers?
Yes, sir.
Yeah, okay, sir.
Okay, okay, I will finish, I think, within next 15-20 minutes. Okay.
Done.
Okay.
Yeah.
Okay, so this was my first part of the talk, where I tried to explain that what are the constituents of the matter, and what are the fundamental forces through which these particles are interacting. Now, as I said that, because the title of my talk, that is something called the hot and dense matter in the heavy and collisions. So what I will now try to answer in the next, that what are the various possible states of matter, and how the transition among these various possible states takes place. Now, what I mean by these states of matter, so all are familiar with this solid, gas, plasma, or liquid, or conductor, insulator. These are different states of matter under different conditions. But here I want to talk about the state of matter at extreme temperature and density, which we used to study in the, for example, high energy physics experiment. And so that I will explain, and then I will explain that under different conditions of temperature and pressure, how different transitions takes place. And to understand this concept of the possible states of matter, first we need quickly to look into two things. The first, I would like to introduce you with this low energy QCD. So what is the meaning of this low energy QCD? If you look into the masses of quarks, so I just introduced you different with the different masses of with the different quarks, and if you look into the masses of quarks, then you will see that up down stage they have the mass very small as compared to the mass of these quark, charm, bottom and top, right? So they are called basically the light quarks, and these are called heavy quarks. Now, if you look into the mass of the protons, for example, as I told you that a proton that is made of two U quarks and one D quark, and if you take the sum of two U quark and one D quark, then that will come about 20 MeV, right? Whereas if you look into the mass of this proton, that will comes out to be around okay, so that will comes out to be around 939 MeV. So why basically that much difference? The mass of proton that is about 939 MeV, whereas the sum of the constituents of the these sum of the masses of these two U quark and one D quark, that is about basically about 20 MeV. So what is the mechanism behind this large mass of the proton? So basically, what is the mass listed here in this? That is called the current quark mass. Okay, and this current quark mass that comes into picture, that can be explained, for example, through the Higgs mechanism. But if you want to explain the mass of the this proton, for example, then what we say that the quarks which are the mass of the quarks, okay, which are making this proton so heavy, those quarks have the mass which is called the constituent quark mass. Okay, and that constituent quark mass, this picture can be explained through something which is called the spontaneous and explicit breaking of the chiral symmetry. So I would like to introduce you with what is the meaning of this explicit and chiral symmetry, because that will be important for us to understand later the phase of the. Okay, let me. Yeah. What I told you earlier, so what I want to do, I want to explain what is chiral symmetry and what is the meaning of this spontaneous and explicit symmetry breaking. So as I told you earlier that we have the Lagrangian of the QCD, and that has one free term psi bar iota gamma mu del mu minus m psi bar psi. Then there will be other term which will involve the interaction of this quark with the gluon. There will be some interaction terms. So in this Lagrangian density, if you look into this term, this is called the mass term. Here m is the mass of this particle which is represented with this psi. Okay, so here this is the mass of the quark basically. So if we take the light quark mass, okay, which is around 5 MeV or 6 MeV, and if we could neglect that mass because that is very small, then this Lagrangian that will be basically symmetric under left and right-handed transformation. And so we say that Lagrangian that is has a symmetry which is called the QCD symmetry, or sorry, this which is called the chiral symmetry. So in the limit when we can neglect the masses of the quarks, then our QCD Lagrangian that will be symmetric and left under left and right-handed transformations, and that property is known as chiral symmetry. However, as I told you that the mass of the proton, for example, that is very large, and that cannot be explained if we only consider the light quark mass. Okay, so it was postulated initially this idea of the spontaneous symmetry breaking that was given by some scientists which are known as Nabbu and Zona Lezino. So they have postulated that the vacuum of the QCD that is populated with quark anti-quark pairs, and because of those there is the spontaneous breaking of the chiral symmetry. So by spontaneous breaking of the chiral symmetry, I means that the Lagrangian of the QCD will have a symmetry, but the vacuum that will not have the symmetry, but that symmetry is broken spontaneously, and that symmetry is broken through the population of the condensates, and these condensates are basically the quark anti-quark pairs. And also, since the masses are not exactly zero, we have to consider those mass. And if we consider that mass, so if we consider this term and psi bar psi in the Lagrangian of the QCD, then this chiral symmetry is again broken, and that is called the explicit breaking of the chiral symmetry. So mass term, inclusion of the mass term in the Lagrangian, that will break the symmetry explicitly. And when we take into account the idea of the quark anti-quark pairs or quark condensate, then the spontaneous breaking of the chiral symmetry will take place. Okay, and through the spontaneous breaking of the chiral symmetry, these quarks, they acquire some mass which is called the constituent mass. Okay, so when we say that protons, they are made of 2u quark and 1d quark, then the mass they have, that is called the constituent quark mass. Okay, that is not called current quark mass. Just taking into account the current quark mass, you cannot explain the mass of the proton or other hadrons also. Okay, so this was the first thing I want to introduce with you, that what is the meaning of this uh, chiral spontaneous breaking of the chiral symmetry. And next, I will quickly look into this experiment in the high energy physics. So basically, in the high energy physics, there are two type of experiment. One is called the collider experiment, where the two beams of, for example, heavy ions or proton, anti-proton beams, they are made to collide in the center of mass frame. So those, there we will have the head-on collisions. Both are the beams, they will be moving towards each other. So if we consider, for example, this kind of reaction, if we have proton-proton, say collision, for example, or proton, they are decaying or they are producing through some reaction to proton and a pi zero meson. Okay, then the threshold kinetic energy which we need for these incident, these proton-proton beams, that should be 67 mega electron volt. You can do some kinematic calculation and you can prove that if we carry out this reaction, this experiment in the center of mass frame, then the threshold kinetic energy which we need, that is much less than in the laboratory frame. And therefore, if we do some experiment in the center of mass frame, or if we do the experiment in the colliders, then more energy can be created as compared to the fixed target experiments. Okay, so in the high energy physics, we have linear accelerators. So linear accelerator, in those basically the beams, they can be collided hand on, or you can have a fixed target and beams are incident on that fixed target. So linear accelerators, they are generally used for the light particles, whereas these circular colliders, they are used for the collision of the heavier particle. By heavier, for example, if you look into the experiment of high energy physics, there are electron positron kind of the collisions, or proton proton collisions. Okay, for example, in the LSC experiment, then you LSC is a large hadron collider. So that is a circular collider of in a tunnel of 27 kilometer. So the basic idea is that when we accelerate the charged particle in the circular motion, then they emit something called the synchrotron radiations. And these synchrotron radiation, they cause the energy loss through these radiations. and this energy loss is inversely proportional to the mass. So heavier the particle, less will be the energy loss. Okay, and therefore in the circular collider, we should use the beams, heavy beams, say proton or hadrons. And if we want to make the collisions between the electrons, say, then we should normally focus on the linear accelerated. Okay, and this is the just a figure which tells us that how different particles are detected. Our modern detector, they have basically different parts. Okay, so if you example for example, if you have a photon or electron, they will be detected in the part which is called the electromagnetic calorimeter. If you have some hadrons, they will be detected in something called hadronic calorimeter. And the neutrinos, they are uncharged particles, they will not be detected through in any of these, and it is therefore very difficult to detect the neutrinos. And there are other experimental techniques, for example something called momentum imbalance, through which we can detect the neutrinos. Okay, so what I want to tell you so what I was telling, that what are the different possible states of matter. So if you consider some system of, say, for example, if you look into the heavy ion collisions, then what is done in the heavy ion collisions, that two beams of heavy ions, say, if we take the example of LHC experiment, in the LHC there is something called ALICE experiment, where lead collisions takes place. Initially they were at 2.76 tera electron volt energy, and later they were at 5.14 tera electron volt. So if we have a system of nucleons, they are collided together. Okay, so if we take the if we have the collision among those particles or nucleons, then at very high center of mass energy, but we can have a state which is called the quark gluon plasma. So how this quark gluon plasma can be created? So there are basically two ways. Either what we can do, we can heat our system, we can supply more and more energy, and when we supply more and more energy, then what will happen? Through that energy, new quark anti-quark pair will be produced. Okay, and we can have finally a state of QGP. The other thing which we can do, that if we have a system of the nucleons, if we that keep on compressing that system, then what will happen? That so if we consider that these nucleons have some wave structure kind of thing, that, and if we are keep on compressing this system, then the wave function of different particles that will start overlapping, and at some time what will happen, that it will become difficult to distinguish between different nucleons, and this system will behave like a free gas of quarks and gluons. Okay, so there are basically two way of producing the quark gluon plasma. Okay, one is either using through the compression or through the heating. So here this quark gluon plasma can occur. This might have occurred in the earliest stage of the evolution of the universe, or this might occur in the neutron stars. Neutron stars, they are the astrophysical objects. These are very dense objects, and here, uh, if the density of the, it is expected that the density in the core of these neutron stars, that is about 4 to 5 times the nuclear saturation density. And this large density, that can also lead to the, through the what I told earlier, that through the compression we can have the QGP. And there are the studies, uh, different pupils are taking, and which indicate that, or they are considering this concept, that there may be the core inside this neutron star, where we have the something called quark matter. And we can also put, and this because we cannot approach to the neutron star, or we cannot go to the early phase of the universe, so how we can study this quark gluon plasma? So that is studied through the heavy ion collision experiments. So what is done in the heavy ion collision experiments, that two beams of heavy ions, they are approached to each other. So for example, as I told you that in the LSC experiment, the beams of lead, they are collided with each other and they move at very high velocity. The collisions takes place say at 2.76 tera electron volt. So at this they have very ultra relativistic speed, and so the nucleons which are undergoing the collisions, they get Lorentz contracted because there is Lorentz contraction at this high relativistic speed. And when the collisions takes place, then after some time, the initial phase of the collision, after what happened just after the collision, that is, that picture is not completely clear. Okay, so that is something called the pre-equilibrium dynamic. Okay, just like the Big Bang. If we look into the Big Bang theory, then we says that okay, we do not know how the Big Bang takes place. Okay, and after the Big Bang, there is something called the inflation era. There it was supposed that the universe grow in some exponential manner, and after that we have the expansion where different phases take place. I mean, initially we can have a phase where we have the free leptons, gluons, photons, and then electroweak transitions takes place. And after that, different transition. For example, there will be a transition which is called the QCD phase transition that will take place, and so on. And after so here along the x-axis, the timeline is given that at what time what phenomena take place and how we came into the present picture of the universe. Okay, so these are basically different these here we can have this quark gluon plasma in the heavy ion collision experiments. So when this heavy ion collisions takes place, then once we have this thermal equilibrium, then here if we have this very high center of mass energy, then what can happen that, as I told you, that when we increase the this energy or momenta, then alpha s, the strong coupling constant, that becomes very weak at high energy. Okay, and therefore we can have a free quarks and gluons. Okay, and then with the time, as the time passes, temperature keep on lowering. Okay, this plasma cools, and then transition take place from the quarks and gluons to something called hadrons. So these quarks in the quark phase, they will combine with each other. They may combine with anti-quark to form mesons, or three quarks may combine to form some kind of baryons. And then we have some phase which is called the hadronic phase. Okay, so after the quark gluon plasma in the heavy ion collision experiment, we have one new phase. This is called the hadronic phase. And so in the hadronic phase, now we have different kind of hadrons. For example, proton, neutron, kaons, pions, etc. And these particles will be interacting with each other, and those interactions, they will modify the properties of these particles. And after some time, as the temperature further lower, okay, these particle, they stop interacting with each other, and we say that there is the freeze-out. So there are two type of freeze-out we generally talk about. One is called the kinetic freeze-out, and another is called the chemical freeze-out. And at what temperature or what density this chemical or kinetic freeze-out take place, that is identified from the experimental observables, which is so different experimental observables, they are observed in different experimental facilities. Okay, so this is just what I told, the various stages of the heavy ion collision experiment. So this is finally the motive of different experimental facilities. In the high energy physics, the various experimental facility, they basically try to understand the different phases of the matter. So this is called the QCD phase diagram, which represent various states of the matter. So what is done here? In the x-axis, I have this baryonic density. In the y-axis, I have here temperature. So so what I told you that in the heavy ion collision experiments, if the collision between the heavy ions, they are at very high relativistic speeds, then we can form a state of matter which is called quark gluon plasma. Okay, so in that quark gluon plasma, we have three quarks and gluons. Okay, and at that time, these quarks, they will be massless, or they have the current quark mass only. They will not have the constituent quark mass, as I told, as I was discussing earlier. The constituent quark mass that comes into picture when we have the hadrons, right? So when we have this light quarks, means we have mass is equal to almost zero, and the matter we have in this quark gluon plasma, that will have a property which is called the chiral symmetry. However, when we come down as the temperature lowers, okay, then there will be a transition to the hadronic phase. So in the hadronic phase, we have now different hadrons. So whatever is shown in this diagram, for example, so what we do experimentally, that we try to go from this side to this side. We want to create in the laboratory, for example, quark gluon plasma. Okay, so in this figure, for example, different experimental facilities are shown. For example, here I have this RIC and LSC. So RIC and LSC, in these experimental facilities, the heavy ion collisions takes place at very high center of mass energy. So medium which is produced in this experimental facility, that is at very high temperature or low baryonic density. Whereas there are the experimental facilities which will be working in the near future as well. For example, this is the FAIR facility for anti-proton and ion research. This is, I think, under construction in the Germany. So these experimental facility, for example, FAIR or NICA, they have the goal of exploring this state of matter. Okay, so people try to understand that when we go from the hadronic phase to the quark gluon plasma phase, then what are different transitions which take place? For example, as I told that when we increase the temperature and density, then from the hadrons, quarks and gluons, they can be liberated. Okay, then at what temperature and pressure, and baryonic density, this transition, chiral transition, will take place. Okay, so by chiral transition, I mean when we can neglect the mass. Okay, and this is one more word which is written here. This is called the deconfinement transition. Deconfinement means I have a hadron. Inside that, I have these quarks. So if I increase temperature or baryonic density, then what will happen that, as I told you, that this different particle, they will start overlapping and it will behave as a free gas, right? But it is not necessary that we have exactly here the massless quarks. Okay, the quarks, they can still have the mass around their constituent quark mass, but they will not be a part of hadrons. Okay, so that kind of transition, that is called the deconfinement transition, and it is all the part of research. These are active topics as of today also, that at what temperature these transitions takes place, whether the deconfinement transition, chiral transitions, they take place at same temperature or density or not. Then this is also something called the RIC BES program. This RIC experiment, that in the RIC experimental facility, the gold-gold collisions, they took place at center of mass energy 200 GeV, and those collisions were carried out in the year 2000. But now, at present, this RIC facility, in this we have this star collaboration, and they are performing the low energy. For example, in the next I have shown, these are the low energy program of the RIC experiment, which is known as BES, Beam Energy Scan Program, where they are performing the collisions at the low center of mass energy. For example, starting from around 5 or 7 GeV to around 18, 19, and so on. Okay, and they want to understand basically that there is something called the critical point, and they want to understand the location of this critical point in the QCD phase diagram. Okay, so that is the basically objective of this beam energy scan program, and also the objective of other experimental facilities which are ongoing, or some of them they will be the future experiments in the high energy physics. Okay, then there are also the interest of the pupil to explore the QCD phase diagram under strong magnetic field. So but is proposed that if we have two heavy ion beams, if there is the off central, okay, collisions, okay, so if we have a beam which these are the charged beams which are undergoing the collisions, and if they have some finite impact parameter, okay, then that can lead to the production of the huge magnetic field. So here I have given the value of the magnetic fields. For example, this is earth magnetic field, and if you compare these magnetic field value, then you will see that the magnetic field produced in the heavy ion collision, that is very large, and this huge magnetic field that can affect the experimental observables. Okay, so that is a part of current experimental research in the high energy physics to understand the what is the effect of these huge magnetic field on the experimental observables. Okay, then in the hadronic phase, but I told you that we have different protons, neutrons, or kaons. They interact with each other, and due to their interactions also, the experimental observables are modified. Okay, so there are different models. For example, here this is the Valeska model, uh, which we can use to study the in-medium property of the hadrons. And with the help of those studies, we can understand the experimental observables which are produced in different heavy facilities. Okay, so with this, now I would like to end my talk, and these are just some uh, basically the benefit to the society, that the aim of these heavy end collisions or different high energy physics experiment, that is not only to create the heavy particles or to understand structure or substructure, but there are other many applications which comes into picture with this advancement. You see that when these heavy ion facilities or different experimental facilities are created, then very advanced technology is required, and that also give benefits to the society. For example, we are all now use this internet, and we used to write this www, and that was first invented in the CERN, Geneva. Here, this computer engineer, he invented this www in order to resolve the problem of the scientist, where they have to deal with the large data on different computers. And in order to solve that problem, he came up with this idea of the World Wide Web. Okay, then these low energy electron particle accelerators, they are also used for sterilizing of the food packaging. Then there is something called hadron therapy. Here, hadron beams, low energy hadron beams, they are used for the treatment of the cancer. So the benefit of that is that when you use hadron beams, then what the energy is carried out by hadron beams, most of the part of that energy, that will be deposited on that tissue which is affected, okay, through the by the cancer. So in the India, for example, this I found during my this Google search, that in India, this is a first this Apollo Proton Cancer Center in Chennai, and they have this paper of 2020. Recently, they have this facility of cancer treatment through the hadron therapy. And I was reading on the internet that by year, I think 2015 or 18, there were only 49 centers throughout the world which use this experimental facility. Okay, so similarly, this is one last, that this is one experimental facility of the high energy physics, JPAR, and one part of that experimental facility they use for the material science and life science experimental facility means. Okay, so with this, I would like to end the.
Thank you very much, sir, for explaining the various concepts of high energy physics in such a detailed and interesting manner. I hope this talk would be helping the students to understand the subject in a better way and would help faculty to deliver their lectures in even better way. So with this, I would ask participants for the questions. Please unmute your mic if you have any query, or let me know if I should read the questions for you. Okay, so sir, actually, during your talk, there was a question. So what is a source of neutrino particles? So, Satbir sir, are you there? He was asking the question actually, so I'm not sure whether he is here yet. I don't see.
He had left, ma'am.
Is he there? He left,
No.
right? Yeah.
Okay,
Okay, so is there any other question?
But we can
okay,
convey, um, he joined almost all the sessions, so we can convey.
Yeah.
okay. So basically, what I told earlier during the beta decay processes, that if we consider that as a two decay process, then we were not able to explain that kind of spectra of the electron beam. Okay, so then the idea of this neutrino came into the picture.
Yes, sir. Thanks, sir. And the talk was very nice and very delivered in a very effective manner.
Okay, thank you, thank you.
Okay,
Thank
thank you,
you
sir.
again.
Okay, thank you.
Okay, sir. Bye bye.
प्रभ मैम रिकॉर्डिंग बंद करना. प्रभ मैम. प्रभ मैम. प्रभ मैम रिकॉर्डिंग बंद करना 1 मिनट. रिकॉर्डिंग बंद करना. वो पहले वाली भी 3 साढ़े 3 घंटे बनती रही.